Okay, then let's start right away. Welcome, everybody. Okay, so I wanted to talk about exercise 103 and exercise 106. I thought there are there's quite a lot of text, so let's see how far we come. Okay, let's start with exercise 103. So in this chapter right now, we're talking about circuit compilers. And you've learned in the last chapter about the different ideas of how to set up the whole statement idea, right? Like how to transform a statement from having it in the algebraic circuit into an R1CS into the quadratic arithmetic program. Sorry, from the R1CS to algebraic circuit to the QAP. Like why I'm getting a little it's really some of them equivalent, some, and then you're getting into the QAP situation. But this was in the last chapter. So in this chapter, we want to understand actually how to write how should we even compile a big statement? Like how do we if I have an algorithm and I want to say I want to put this algorithm into a SNARK, how do I write it down? And then how would it be translated into an algebraic circuit and R1CS and then to a QAP? Okay, there's some people raising their hand, I think. Bassem?
Hi, sorry. Whoops.
Yes.
Sorry, can you hear me?
Yes, I can.
Hello.
We can hear you.
I can't hear anyone.
I can hear you.
I know what he wants to say.
Yeah, hi, can you hear me?
Yes.
Okay, so I'm a little confused. Weren't we supposed to be still on chapter 5 right now?
Yeah, we skipped one week last week.
Right, and then
prepared the wrong exercise, but it is fine. You can.
Yeah, it's fine. I mean, I just want to confirm where everyone else is. I started chapter 6, but I guess we jumped to chapter 7 already. And
yeah, I thought Jasper told you, but no.
No. Oh my God, I'm so sorry. I looked at the project plan, at the plan that's pinned in the channel, and it said chapter 7. So I thought, okay, we're ahead, and okay, that's really unfortunate. That's why I texted you earlier. I was like, are we really on chapter 7? Should I prepare the exercise for chapter 7?
I mean, we can talk about QAP. At least I'm fine with that.
No, actually, we're I just I think this match is still if you started reading about chapter 6, the statements,
Yeah.
that's good because I prepared I think the circuit compilers matches kind of the statements chapter. So if you're on the beginning of chapter 6, that's maybe it matches already. It's a little bit ahead because this is chapter 7.
okay, that's cool. I'll try to keep up with everything then.
Yeah,
okay, so
let's
maybe
just do that.
Okay, maybe I'll just quickly go over what I have, and then we can revisit it in the 1 week or when you're there. And so in general, if you started chapter 6 about statements, you might have read about the rank 1 constraint system and the algebraic circuit. I hope that's correct at this point. And there we're talking about how we can actually we need to have a formal language such that we can actually write a statement down for the SNARK, right? Because what is a statement even? So I'm just trying to get into the chapter 6 language. So I hope that's okay. So in chapter 6, we're introducing instances and witnesses, and then we're talking about how to write down a specific statement. And my colleague introduced there the rank 1 constraint system and the algebraic circuit. And I can just show you maybe because, yeah, it's really a little bit unfortunate that I thought that we are on chapter 7 now. Because what we'll later do is we'll write the circuits in this specific language. And we'll have things like these. I don't know if I hope you see it. This will be algebraic circuits. And from these circuits, we can actually prove that something is true. And we can specifically say one thing should be input, one thing should be output, one thing should be private, one thing should be public. And this will be the idea. And so this is what I prepared, but I think it's a little bit ahead if, we have not yet talked about algebraic circuits and rank 1 constraint systems. Chen Yang, I'm so sorry. Like, what do you think? I think we should skip then the exercise session. Yeah.
I am happy with this. I'm not sure about other people. I actually have one question for you. Like I was confused. So so I know that in theory we can turn like every NP problem into arithmetic circuit, right?
Yes.
But like is it so what's the like a theorem stating that maybe? Yeah, because I know it as a fact. I'm not sure like if that statement can be proved.
Okay, so I think there is a paper on this. There is theory behind it. I don't have it right here right now, so I don't have like I don't have a reference right now for this, but there is theoretic work. I can send you later with the idea behind it.
Sure.
But I have to find it. Okay, so we're all on the same page that we're actually doing chapter 6, right? Then I can maybe show you something else that I've prepared for another course, if that's interesting.
Yes, I think.
Okay, so I'll stop sharing these exercises and I'll share this slide deck instead. Okay, let me just go into the correct. Okay, so I think this might matches kind of the statements chapter. I hope you see it. Okay, so kind of the statements chapter is all about like what you can prove in a SNARK. So we've learned all the elliptic curve things. We've learned like, the algebra, all of that. But now the question is, I want to prove something, right? So there's, for example, this person called Paula. And the question would be, can I prove the sentences in a SNARK? Like I know a pre-image to a hash value. I know the factorization of an integer. I can buy this beer. My mom is the best. Like, what of these sentences can you actually prove? So this is kind of the idea about the statements chapter. Like, what can we actually put into the SNARK? So 2 of them you cannot actually prove because I can buy this beer. Like, do you have enough money? Are you old enough? Like, this is all questions that are hard to answer. And my mom is the best is a subjective statement because everybody would say their mom is the best. Maybe not. But the first 2, they sound mathematical and they sound like something we could put into a proof. So what we did in this chapter is that we have to translate all this like words that we want to prove into a zk-SNARK. So we're building an alphabet, we're building a set of finite tuples, and then we say that a language is a subset of this set of finite tuples. And there's a deciding relation R that decides if that deciding the rules and the grammar of a language, just like it is with our language, where we have an alphabet and we have tuples, words, or just words like Anna or Liz or something. And there is a deciding relation that says this is a word and this is not a word. So we do a similar thing. And we have instances and witnesses, which we are denoting here by I and W, which mean that some are public and some are secret, the witnesses, and instances are public. And if this relation for the instances and witnesses holds, then that specific IW tuple is in the language. So this is kind of the idea of this chapter. And then I use the toy example here, where I'm doing the 3 factorization here. So we have 3 numbers, x1, x2, x3, and these multiplied should be x4, and they're all in F13. So this is not practical. This is not saying anything at all. It's just to like show this kind of idea. So we do a Siding relation where we take instance values and witness values, and we decide if it's true or false. And it is in this specific setting, the public input, we have 1 public input, and with 3 private inputs, which I'm setting now. Like I'm just saying that we have 3. And these are like the x1s, x2s, and x3s. And this holds if it's true that the instance that I give with the 3 secret inputs, if they multiplied are the instance. And for every other things, it doesn't hold. So that's kind of the idea. And we go through different computational models. So we have this thing in our language, this relation. And this relation now, we have to, like, it's still just a relation. We need to make it, we have to understand it in a computational model. So we'll have an algebraic circuit, and then we're going to transform it into a rank 1 constraint system, and then we're going to transform it into a QAP. And I'm just going to show the first part, and maybe then we can like use questions, because I was not really prepared, so it's a really bad. So it's like I'm spontaneously doing as much as I can for this chapter, but yeah. So an algebraic circuit, if you write the book, if you start with chapter 6, is a directed acyclic graph. Directed means it has arrows, it goes in one direction, meaning you cannot go back. If you ever heard of like graph theory, directed graphs go in one direction. There's like a sink, and there's a source, so you go from source to sink. Acyclic means there's no circles, and we're over a field F. So we have outgoing nodes and we have incoming edges. Incoming edges to the sink nodes and outgoing edges to the source nodes, from the source nodes. And there's exactly 2 incoming edges always. And we have nodes which are addition or multiplication nodes. And this is what we call arithmetic gates. So this is the very fast understanding. Like, I think this text does not help at all. Like, if you see it once, you will understand much better. So what we will do, for example, with this example, we can understand the multiplications that we have here. In this setting, we have 2 multiplications, x1, x2, and the result of this multiplied with x3. So we have 2 multiplication gates that we need, and we can build an algebraic circuit. And in this presentation, I made people draw it, but in the end, it will look something like this. So we have x1 and x2, and 2 incoming edges to the multiplication gate, and 1 outgoing edge. And that outgoing edge is going to become the incoming edge to another multiplication gate, which is going to be multiplied with x3. And then we have the outgoing edge, which is the instance. And so this would be an algebraic circuit. Okay, so I think this might be helpful, might be not. But this would be the idea of this chapter. Kenyang, what do you think? Like, should I continue? Should we discuss questions? What do you prefer?
You can continue. I like it.
Okay, I hope everybody else as well. It's like, you know, a presentation of the chapter, so that's maybe helpful when you read it. So, like I showed you now how to represent this problem as an algebraic circuit, right? So we're presenting this 3 factorization as an algebraic circuit. But wait, there is no numbers. Like, how do I actually prove something that, you know, I have these 3 values, x1, x2, and x3, that if I multiply them equal x4? So what you do is here, so this is kind of the setup phase. Like, if you look at like SNARKs, this would be the setup phase. You set up the problem. And now in the prover phase, I would actually give you assignments to those edges here. I would say, I know x1, I know x2, I know x3. Like, I would assign these edges here with numbers. And then we can see if this assignment works. And this is the prover phase of this setting. So this is just setting up whatever problem we have. We have to set it as an algebraic circuit. We have to understand it as an algebraic circuit. And then we can prove something in it, let's say. We have to still do some things, but this is the idea. So as I said, like, how do we prove this now? We have to like take something IW and see if it's a valid assignment. So here in this example, maybe you can tell me, like, I have like the statement that I want to prove now, the like S. What I'm saying is the instance is 11, and the W1, W2, W3, W4, they are 2, 3, 4, and 6. So we would have here 2, 3, 4, and 6, and the instance is 11. So is this a valid assignment or not? Maybe you can write in the chat or tell me or something like that.
Can you repeat the question?
Is this S here with 11, yes. 2, 3, 4, 6, is this a correct assignment to the circuit? Is this a valid assignment or is this not a valid assignment?
Of course not, right? Oh, wait, what's that I? I'm a little confused. What's that I?
Okay, I love that we're, yeah, so you have to remember we're in F13, right?
Oh, okay.
So this algebraic circuit is built over F13.
So I see. Oh, okay.
Yes. So
24 modulo 13.
Yes, it is 24 modulo.
Oh, yeah, that's correct. Okay.
Yes. So for this 3 factorization problem, if I give you the numbers 2, 3, 4, so 2, 3, 4, the intermediate value is 6, like if this is the witness and I have the public instance 11, this would be a correct assignment to the circuit, actually. So this is a correct assignment because 24 modulo 13 is 11. So that's correct. I have another example here, like now you should be much faster. For example, if I give you the witness values 2, 3, 4, 7, and 8, is this a valid assignment or not to this algebraic circuit?
This one is incorrect.
This one's incorrect, exactly. Because 2 times 3 with the multiplication gate is not a valid assignment to W4 equals 7. And also here, we can see that. So just for you to understand.
Can I ask a follow-up question?
Yes, please. Mm-hmm.
How do you decide on what the instances will be? Or could we also add W4 as an instant instead? Like, would that be wrong or incorrect?
That's a fantastic question. So no, like this would be not incorrect. So this is just set by me for this example. And for some, like you have to, like for all the circuits that we'll see, like this assignment is just made by the person setting up this problem. So when I set it up, like when we wrote down the algebraic circuit before, I just declared I was like, here, this is going to be the circuit. So I just declared what edges are going to be W's, meaning witnesses, and what edges are going to be instances. Because in general, like this is just a 3 factorization. I could have also picked that x2 is the only witness and x1 and x3 are, for example, public input. Things like that. But I just wanted to make like a very basic example. So this is why I chose it like this. This example is really like a toy example. So there's no real mathematical worth in it. You cannot like prove anything with it. It doesn't, it's not giving you any kind of like nice zero knowledge proof. I just picked it because from here we have 2 multiplication gates. So this is a minimal example to build an Error-1 CS with 2 constraints. I'll show you in a bit. So this is why I picked the 3 factorization instead of the 2 factorization. But yeah, this is the idea. So you can pick it like you want, but yeah, if you make a bigger circuit, like this is what chapter 7 is then about, you have to actually like see what exactly is witnesses, what exactly is inputs. And in chapter 7, like this is just to understand the concepts. In chapter 6, where you understand the algebraic circuit, you understand the concept of it, you understand the concept of the rank 1 constraint system, you understand the concept of the QAP. And in chapter 7, we'll then have like bigger problems where we actually want to like have problems which we actually want to put into this algebraic circuit, and then we'll understand what should be witnesses, what should be instances, sorry, what should be public, what should be private, how to actually make sure that something is a Boolean, how to make like an inverse of something, you know, how to think about bigger algorithms and how to put bigger algorithms into the structure. Because this structure, it's just a toy example so you understand what should be an algebraic circuit if people talk about an algebraic circuit, just so you see what it is. And if people talk about an R1CS, just so you see what it's supposed to be. So this is the idea. And like I'll just like continue here, but you can stop me anytime if you want to like, you know, talk about something else. So from this algebraic circuit to actually like make all the elliptic curve operations that we have seen, like how do you make the elliptic curve operations over like some arrows and some edges and some nodes? You cannot do it, right? So to make the elliptic curve, to use the power of the elliptic curves that we learned in the chapter before, we have to transform the algebraic circuit into an R1CS and then into a QAP. So this is kind of this is where kind of magic happens, because the algebraic circuit is the statement that we wanted to prove, and then we're going to transform the statement to translate it. So what we're doing is we're going to build a so-called R1CS, a rank 1 constraint system. It has a lot of equations. K is the number of constraints, meaning the number of equations. So in this case, like I wrote 3 dots, so it means I have like a lot of, you know, there's K in the subset here. So it means like I have K equations here. And then we have a big multiplication with 2 big brackets where we set all the instances and the witnesses here. And we kind of like just write them all down. So I are the instances, W are the witnesses, and we set them. So A1, A0, B1, B0s, and all of them, they're values where we set them. And normally a lot of them should be 0. So this is kind of the idea, that a lot of these values should be 0. But I'll show you with our minimal example. But this is how the definition of it is. So from this thing that we have seen, we have 2 constraints actually in the end. So what we have is that W1 times W2 should be an intermediate value, which is W4, right? And this intermediate value multiplied with W3 should be the instance. So that's 2 constraints. So how do we translate it now into this form? So what we have is we have W1, so we should set this value to 1, and W2. So we should set like somewhere here where the dots are, another value to 1. And this should equal W4, like 1 times W4. So the C should be 1 here, like 1C should be 1. And the other C's are going to be 0, the other B's are going to be 0, and the other A's are going to be 0. So this would be the first constraint. So let's see how I wrote it here. This is actually exactly what I wrote. So we have 1 instance. So this is the constants here. The first value is the constants. And the second one is the instances. So the instance is not set here, so we can just make a 0 here. And we have 1 times W1 times 1 times W2 equals 1 times W4. So in this brackets, as you see, we have always a value for the constants, a value for the instance, and 4 values for the witnesses, because in my example, I have 1 instance and 4 witnesses. And for the second constraint, we're going to do the same. We have 1 times W4 times 1 times W3 should equal the instance. So this is the rank 1 constraint system. The rank 1 constraint system is this equations. So this is how it looks. It's the values that we have. So we have here the A, like this is the first constraint always, like this first line, the second line, and the third line. The first line, the third line, and the fifth line. This is the first constraint, and the second, fourth, and sixth line are the second constraint. And as you see, a lot of these values are 0, just but 6. So this is the R1CS. Any questions at this point for this minimal example?
Yeah, so depending on how we formulate the problem, we could have a different R1CS for the same.
Yes. Mm-hmm. Very true, exactly. In my example, I have 4 witness values, right? You asked why 4? Like, cannot be like something else, the public input? You know, why is all 3 of them witnesses, and then the intermediate value is another witness? Like, why? And you're absolutely correct. I could have here, I could say that, for example, witness 3 is an instance, meaning it's public. So then I would have here 2 instance values, so the I1 and I2, and I would only have 3 witness values. Does that make sense?
It does, but I'm just, I cannot convince myself that the output would be the same then, or like we would always get the correct output. I don't know. Is there like a one-to-one correspondence or between different circuits for the same problem?
No, that's a good question. So the thing is, the circuit, wait, let's go back to the circuit. The circuit looks similar. The only thing is that the edges are denoted by a different thing. So we would here have, for example, as I mentioned, if x3, for example, if I say, oh, x3 should be public, then here there would be an I. There would be I2, and this would be W3. Okay? And why I'm saying this, the circuit looks kind of the same, and it seems very, very similar. It just means that some values are going to be private and some are going to be public, others than the ones I put. And this is going to be important because in the rank 1 constraint system, I very, very much exactly like say which of them are public and which of them are not because of the location of the I's and the W's. So there's A and B values, right? And the A and B values, they're enumerated. So if I know that this column here, this is the constants. And this here, this is the instance. And this is the instance, and this is the instance. And these 4, these are the coefficients for the witnesses. So if I make it different, then like I will have 2 columns of instance values and 3 columns of witness values only. Like it will be different. And then you will see in the QAP, like when we'll now make a quadratic arithmetic program out of it, it will look different. And this means for the SNARK, just for you to think about the SNARK, that we can set in the SNARK, we'll have, this is public, and you don't have to provide a witness for it, but this will be witnesses. So it's kind of like you have to be very clear on what's public and what's private, and then you can build the QAP according to it. Does that help?
Yes, definitely. So would this be would there be like room for dealing with efficiency here? Like, does it matter how you select these values? Would that come under efficiency? I'm not sure. Or would one R1CS circuit be better? Or sorry, one way that you have selected these values, would one be more efficient than the other in that regard?
I think so. Okay, so there's 2 comments that I would make here. So first, like instead of efficiency, normally this is being thought of as in terms of security, because ZKPs, they have the zero knowledge property, right? You want to have the witness, you want to have things nobody else should know, and then you have things which are public, so people can know them. So normally people don't really it's more about knowing what you want to be a witness. So that's how you set the values normally. And then another thing, the other comment that I want to make is that this is gross 16. So this is like what we're discussing here right now, the algebraic circuit, the R1CS, the QAP. This is all for gross 16 zk-SNARKs. This is the so-called arithmetization of gross 16. Arithmetization meaning how you make a statement into something with polynomials, something where we can use the elliptic curve operations on top. In Planck and Planckish systems, you have a different idea. So what you do there is you build a table, and it's more like a processor which is going through like the table and going through the lines of the table. And in the book, there's examples now for it, but when I did this presentation, I did not have it yet. So this is just the gross 16 idea. And it's quite helpful to understand the basics. When you have the Planck thing, you can do much more with efficiency. Because as you've seen now, like in my example, I only have multiplication and addition gates, meaning like everything is very complicated. Imagine the elliptic curve operations that you've learned in the past session with like addition multiplication gates, like in a field, like it's super complicated. It's a lot of like constraints because you always have to like break down to additions and multiplications. So what is happening with Planck is that with Planckish systems, you can build custom gates. And this custom gates mean that you prove something for a specific custom gate, and the custom gate can be like a different operation. It doesn't have to be only addition or multiplication. So there you get a lot of efficiency. So this is quite nice. And also with the setup that I mentioned here you need the setup. That's it's not just inefficient, but it's also a security problem. Whereas with blocker systems, you can, like, it depends, but you have like a universal setup. So this is kind of like the idea. I don't know if this helps, but yeah.
Yes, that helps. Thank you.
Sure. Maybe I'll just like finish the QAP idea, and it will be easier to read. The chapter might be easier to read then. So what we're going to look at is we have to translate now this R1CS, which is just this table of A, B, and C values, like just those A, B, and C values, the coefficients. We have to translate this now to actually polynomials. So what we're going to do is we are going to build polynomials out of this A, B, and C values. And I'm just going to really quickly go over it because I think the best it is just to go through this example. Is we're going to build a target polynomial, and the target polynomial will have as many, the degree of it is as many as like constraints we have. So in this setting, we have 2 constraints. So I'm just picking 2 random values from F13 for the first and the second constraint, and I'm going to build a target polynomial. And then I will set, I will use the coefficients of A's and B's to set them for my A, B, and C polynomial. And I can do a Lagrange interpolation. So I wrote this here. Maybe you have to repeat it from like your math basics course. So if I have 2 points, I can, from these 2 points, like in this setting, I can build a degree 1 polynomial. It's kind of like the idea of like, I have different points and you can do a Lagrange interpolation to get a polynomial equation. So this is what is happening here. And so we can get the polynomials. And this, in the setting you see, nearly all polynomials are 0, but only A2, A5, B3, B4, C1, and C5 are a polynomial. And they're a degree 1 polynomial because we have 2 constraints. So we get a kind of like -1 degree polynomial. So this is kind of the idea behind it. And from this quadratic arithmetic program, so this is kind of like what happened. This is the summary. Can maybe zoom a little bit in. So what we had is an algebraic circuit, and we set different things to witnesses and different things to instances. And from this, we wrote down the constraints, and we wrote it in this R1CS form, meaning that we kind of set exactly what variable we need, what witness we need for the first constraint, and what instance we need for the second constraint. For example, we only had one, so just this one. And from this table, we then, through Lagrange interpolation, build polynomials where we have an A0 polynomial, a B0 polynomial, and A1 polynomial, A2 polynomial, which you see here. Do you see the A2 polynomial? Because we didn't have zeros here, we actually got something out of it. So this is kind of the summary of the chapter for Gauss 16, and I hope this helped. Sorry for not preparing the right exercises, but I hope this was still very helpful. Chinyoung, I'm so sorry, but I hope this was helpful. So let me know if I can help with anything more. I'll stop sharing. And yeah, this was it for me from Least Authority.
Yeah, this is very helpful, much more helpful than going over elliptic curve exercises. So I have a question. So in my code, I think I use a Lagrange interpolation for turning CS to QAP. Yes, go ahead. We can hear you. What? Oh, I was saying, so I use a Lagrange interpolation in my code, right? But I think in practice, you can use something like FFT to speed up the process. Is that correct?
Yes, it really depends. So normally, like when you use like Circom or Socrates or something like that, they will do this compiling for you, right? Like you will write your statement in their programming language, and they will compile it to polynomials for you and do like the whole like proving stage for you for the instances and witnesses that you gave, I have not looked into the code, but I don't think they're like, I'm not sure, but there is definitely options to do it in a different way.
Okay. Yeah, I think Circom is still under development, so everything can change in the future, maybe. I have no more questions. So what about other people? So any question for Anna?
Just, would it be possible to get access to these slides?
Yeah, I can cut them from the presentation and post them in our Discord. Yeah, sure. I did them for a course I gave at some point, so yeah, I can do that. Sure.
Thank you.
Of course. I also see a question from Liquan in the chat. I'm wondering how to map the ABC to the polynomial. Yeah, I can, like, if you want, I can quickly go over it, but if that's interesting. Chinyang, I don't want to...
Map ABC to polynomial. I think it's just Lagrange interpolation, right?
Yeah, I can show you. Maybe it's...
Yeah, so it's like you just from the R1CS matrix, then you pick out like every column vectors, and then you do Lagrange interpolation on them. So you have a few, like a series of polynomials.
Yeah, I can show you. So you have like the one thing on the left. That's the assignment, right? That's the R1CS assignment. Like which, this is the first witness. This is the second witness here, B13. So we're using the A2 values here. We have 2 points, and we're going to use, like, I picked the target polynomial, right? I told you about for the 2 constraints, and I just picked random values. M1 is 5 and M2 is 7. And this is going to be the x values, 5 and 7. And then we're going to use the assignments here for 1 and 0. So we know that 1 point on the A2 polynomial, just concentrate on the A2 polynomial as for now, that 1 point is going to be on this polynomial is going to be 5, 1, and the other point is going to be 7, 0. And this is just for the A2 polynomial. For the A1 polynomial, we know that 5, 0 should be 0. The point existing on this polynomial is 5, 0 and 7, 0. Okay, so let's concentrate on this polynomial, and how we do it then is exactly as Chinyang was saying, through Lagrange interpolation. So we have 2 points because we have 2 constraints, and we're going to build a degree 1 polynomial from it. So we're going to concentrate on non-zero polynomials, so that's why I picked A2. So we know that there's a set, like as I mentioned, 5, 1 and 0 and 7, 0, because, you know, like the first, like A2 1 was set to 1, so that's why here's a 1 and here's a 0. Okay, and then we can use the Lagrange interpolation where we put in the values. So we have these. We're putting in the A values, and we're going to use the different like x values or m values here. So 5 minus 7 and 7 minus 5. And then we're getting this equation, Euler modulo 13. And we have to do some modulo 13 arithmetic, and then we get 6x plus 10. And we're doing similarly the same thing for A5x. And actually in this setting, like, just because I picked this very simple example to show in the presentation, you see, like, here we have 5, 1 and 7, 0. And here we have again 5, 1 and 7, 0. And here we have again 5, 1 and 7, 0. So actually, these 3 polynomials are the same, and these 3 polynomials are the same, just in this example, because it's always 5, 1 and 7, 0. So this is how we get here the 6 polynomials, and 3 of them are the same, and 3 of them are the same. You can read about the Lagrange interpolation if you want to understand better. So this would help, I think, just reading about the Lagrange interpolation, what it means. It's just a mathematical construct, and as Chinyang was mentioning, there's also the fast Fourier transform that you can do, because normally we have a lot more, like, I just have 2 constraints here, right? But normally it's a lot more constraints, and you want to build a polynomial from it. So, you know, it's going to be a much bigger degree. It's not degree 1. Here we have just a line, right? Yeah. Okay, wait. Lagrange looks clear, but the mapping, the number of coefficient looks confusion. The mapping of the number of coefficients.
Yeah. I can answer that question. So basically, you just from the R1CS matrix, you just pick out a column vector, right? So you have like a vector, and then you just say, for example, the vector is A, B, C, D, E, and then you just say, I do Lagrange interpolation for 1, A, 2, B, 3, C, and blah blah, like that. So basically, like what I mean is, the x coordinates are always fixed. So it's like 1, 2, 3, 4, 5, and then you just change the y coordinate, like according to the column vector.